video, we'll visit a new concept called integration by parts. And this concept is just another one of the tools in the arsenal that we have to solve uh, integration problems. And the formula is given to us here. And the formula basically tells us that we have two functions, u and dv, rather u and v, and they are being multiplied under the integration sign, and we're basically trying to find an easy way to solve those two uh, those two um, rather sorry we're trying to find an easy way to solve the integral using this formula. And I think it makes it a little bit more easy to understand if we use a few examples to make sense of what the question and how the integration by parts usually works. So I think we'll just use we'll just use a few examples to illustrate how we can actually use this formula to solve integration problems, and hopefully that makes it a little bit more understandable. Right, so let's make some room. Right, okay, so let's start with our first example, dealing with the integration of x times e to the x. Right, so that's the first example that we have to deal with here. And the way we deal with it, if we look back at the formula that we have, we basically, and if we associate this example with this formula, we basically have to decide, right, which function will be u and which function will be our v. Right? So let's say that for the sake of this example, we use u to be equal to x. And let's say that we use our dv to be equal to e to the x dx. Right? That would mean that our v will just be equal to e to the x, and our du will just be equal to dx. Right? So now, going back to the formula, if we apply this, we'll have that this integral x times e to the x dx, looking at the formula, will be equal to u times v, right? Meaning x times v, which is e to the x, minus the integral of v du, which is e to the x, times du, which is just dx. And this is further equal to x times e to the x minus the integral of e to the x is just e to the x, right? Plus a constant of integration t. So that is our final answer for this particular question. So as you can see, it's once you understand the concept, it's an easier problem to sort of understand, and it's even easier when you apply it to examples. So let's look at the second example and see if we can solve that as well. So we have the integral of x squared times e to the negative x dx. And here, let's assume that we use our u once again to be equal to x squared, and we use our dv to be equal to e to the negative x dx, right? That would mean that our du will be equal to 2x dx right? And our v will be equal to negative e to the negative x, right? And because remember that v is just the integral of e to the negative x dx, which is negative e to the negative x, right? So if we take it back to the formula, we have that this integral is therefore equal to u times v, which is just x squared multiplied by negative e to the negative x minus the integral of v du, right? So which is negative e to the negative x times 2x dx, which is equal to negative x squared times e to the negative x, right? Minus right, it's going to be minus minus, so it's going to be plus the integral of e to the negative x times 2 times x times dx, right? And as you can see, we have a case where we have the same form as the original integral. So we have to use integration by parts again, right? So using the same concept, let's try to solve the integration of 2 times x times e to the negative x dx. And if we assume that we let u again be equal to x, and we let our dv be equal to e to the negative x dx, once again, we'll try to leave out the 2 because it's a constant and it can be left out of the integration. So with this substitution, our v will therefore be equal to negative e to the negative x. I'll leave out the constant of integration for now because we're still doing the actual integration. So I'll leave it out for now. Sorry. And leaving it out will we'll see that this is therefore equal to, right, if we apply it, our integral becomes, right, 2 times e to the negative x times x dx is therefore equal to 2, right, multiplied into u times x, which is x times negative e to the negative x dx. Oh, there's no dx, sorry. No dx there. Minus the integral of v du, right? I forgot to say du is equal to dx here. So v du, which is therefore negative e to the negative x dx. And this is therefore equal to 2 times x, will be negative 2 times x times e to the negative x plus, right, there'll be a minus minus, so plus 2 multiplied by the integral of e to the negative x, which is just negative e to the negative x plus our constant of integration c. And therefore this is equal to negative 2 times x times e to the negative x minus 2 times e to the negative x plus c, which is our final answer for this problem. Right. No, rather it's not our final answer, sorry. We have to take it back to the original integration. So the original integration is x squared times e to the negative x dx, which we found the first part to be negative x squared times e to the negative x plus this integral, which basically means plus negative 2x times e to the negative x minus 2 times e to the negative x plus a constant of integration. Right, so that should be our final answer. And yeah, so this is what our final answer should look like. So now let's take this further for the third example, where we have the integration of ln x, which, just like the others, we can clearly see that is not easily solvable with the previous method that we are familiar with when solving integrals. So we have to use integration by parts here, and we have to decide, right, how are we going to do the substitution. So first, we'll have to clearly note that the integration of ln x dx is just the same as the integration of 1 times ln x dx, right? And bearing that in mind, we can let our u be equal to what? Let's, for example, let our u be equal to ln x, and therefore our dv will be equal to 1 dx, right? That means that our du will be equal to 1 over x dx, and our v will be equal to x, right? And what that means is that the original integral of ln x dx will therefore become u times v, right, which is x times ln x minus the integral of v du, which is 1 over x times x dx, which is equal to x times ln x. And we can clearly see that x in this part of the integral is common, so we can simplify it, and we're left with the integral of dx, which is x. So this is minus x plus the constant of integration. So that is our final answer for the integral, right? So as you can see, the more you practice with these examples, the easier the concept of integration by parts is. Right, so moving on, let's look at this example. We have the integral of e to the ax times sine bx dx. And we're trying to find, to use integration by part to solve this, right? So, using that logic, we have to determine what do we want to use as our u. So, let's say, for example, that we let our u be equal to e to the ax, and our dv be equal to sine bx dx. Once again, this substitution, so the functions that you choose to be u and v can work either way, right? So basically, the more you practice, the more you know which way would lead you to an answer faster. So if you go back to the previous examples that we've done, and you try to switch the substitution around. So let's say, for example, instead of letting u be equal to ln x in the previous example, we let u be equal to 1, right? And then we let our dv be equal to ln x. So you can try that and see if it gets you somewhere. But in most cases, you'll see that one method is particularly longer and more complicated than the other. So you sort of have to do it multiple times to get the gist of it, right? So that's that. Moving on. So let's let our substitution be this. And that means that our v here will just be negative cos bx over b. Right, there's no dx. Right, and our du will be equal to a times e to the ax dx. And knowing that, we take it back to the original integral, we'll have the integration of e to the ax sine bx dx is equal to u times v, which is just equal to e to the ax multiplied by negative cos bx divided by b minus the integral of v du, which is negative cos bx divided by b multiplied by a times e to the ax dx. And if we do that, we have that this integral is just equal to negative e to the ax cos bx all over b minus minus, so that's that becomes a positive. Sorry, let me just fix that. All right, so this is equal to negative e to the ax times cos bx all divided by b minus minus, which is plus the integral of a over b multiplied by e to the ax times cos bx dx. Okay, so we can try to solve this separately because it's another case where we have to use integration by parts to try and solve it. So if we let our original integral be equal to I, okay, so just so we don't confuse ourselves, because we have a second integration by parts into an original one, so it might be get confusing. So let's this original integral be equal to I, okay? It's represented by I. So now we're trying to solve the integral of a over b multiplied by e to the ax cos bx dx. Now we can leave out the a over b because that's a constant, and we can try to work with the integral of e to the ax times cos bx. And in that case, we have to use the same substitution, a similar substitution as the one we use for the first integration by parts, right? So that's one of the sort of unwritten rules that you have to use. So if for the first case we let our u be equal to e to the a, so our second integration by parts we have to use the same logic. That's u be equal to e to the a, and our dv be equal to cos bx dx, right? And the reason why is if you switch the substitution, it might make the entire thing even more complicated, or even you might even get stuck at some point. So it's always better to stay consistent and use the same sort of substitution that we used before. right? Especially when you have an integration by parts within another integration by parts. Right, so now that we have that, it means that our du will just be equal to a e to the a dx, and our v will be equal to sine bx divided by b, and that means that if we go back to the original integral, which is a over b times the integral of e to the ax cos bx dx, that is equal to u times v, which is e to the ax times sine of bx all divided by b minus the integral of v du, which is sine of bx divided by b multiplied by a times e to the ax dx, right? And this can be simplified to be equal to e to the ax times sine of bx over b minus, we have the common factor a of, the constant factor a over b there, so we can take it out. And we have the integral now of e to the ax times sine bx dx, which, if you remember correctly, was our original I integral that we had there, right? So using that logic, and if we let that, means that this integral here, this integral that we have here, this integral that we have here is our I, right? So if we take it back to the original I integral, so I is equal to what? We found that it was equal to negative e to the ax times cos bx over b, right? So negative e to the ax cos bx over b, right? Was plus our second integral here, so plus a over b times the integral of e to the ax cos bx dx. But we found that this integral is equal to that, right? So this can be rewritten as negative e to the ax cos bx over b plus, right? Obviously here we have an a, rather, so, sorry. We have a over b there that is multiplying this entire thing. So this will just be equal, therefore, to a over b multiplied into e to the ax sine bx over b minus a over b multiplied by the I integral that we had there, right? And therefore this is equal to, so we have I here, and we'll take the terms in I on the left hand side. So we have I plus what? Plus we have the a over b here multiplied into the a over b there, which is a squared over b squared. So we have negative a squared over b squared I. Taking it to the left-hand side, it becomes positive a squared over b squared times I. And we're left with, on the right-hand side, negative e to the ax times cos bx, right? Bx divided by b plus a over b squared, right, times e to the ax times sine bx, right? We can take out I as the common factor there. We have 1 plus a squared over b squared. And on the right-hand side, we have negative e to the ax times cos bx over b plus a over b squared times e to the ax times sine bx. And therefore, this is further equal to I, which is our original integral, which was e to the ax times sine bx dx is equal to negative, right? Negative e to the ax cos bx all over b plus a over b squared times e to the ax sine bx all over 1 plus a squared over b squared. And you can simplify this further by putting the denominator to some common factor, and then you sort of divide and cancel with the a and the b's, and you see what final answer you get. So there's a way to simplify this further, and I'll just leave it for you guys to attempt. Right. So, but that's it. That's basically it for the examples that we looked at. So these examples that we looked at today were just focusing mainly on integration by parts for indefinite integrals. So integrals with no boundaries and limits. So what we'll do is in the next video, we'll be looking at integration by parts that for definite integrals now, where we have boundaries and we have to substitute after doing the actual integration. So that's what the next video will cover. So thank you for watching, and please give a thumbs up to the video if you enjoyed it, and stay tuned for the next video. Thank you so much. Bye.